Hi guys, we're looking today at the uses of radiation. So what we're going to do is first off, you just need to know the different uses of radiation. We're going to look at how the different applications work, and then we're going to look at how the properties of the radiation are exploited for these different uses. So let's just go through the properties. Remember, all three of these come from the nucleus. When a nucleus decays, so you've got alpha over here. Alpha is made of 2 protons and you've got 2 neutrons. Charge of alpha plus 2. It's the most ionizing because it's got the largest mass, the largest momentum. Therefore, it can more easily remove an electron from an atom. It's not very fast. The range is quite small as well, a couple of centimeters in air, can be stopped by things like paper, skin. So then we've got beta. Beta is the fast-moving electron, has a charge of -e. It's less ionizing than alpha, but it can travel further, travel about 50 centimeters, maybe a meter in air, can be stopped by 3 to 5 millimeters of aluminium. And then you've got gamma. So gamma is massless, is chargeless, it is electromagnetic radiation, it is just energy emitted by the nucleus. It can be reduced by lead in concrete, very, very difficult to stop. So here are the different uses. So this one here, this is measuring paper thickness. Now, I know you're thinking, who the hell wants to measure the thickness of paper? This is for someone like a paper factory that's making paper, not just anyone. You know, if you wanted to, a teacher wanted to measure paper in the lab, it's for someone actually selling paper. Think about it. They want to make sure the paper is the right thickness. If it's too thin, they've got a bad quality product that's going to be sold. If it's too thick, then they've got really thick paper, and therefore they're using more of their resources to make the paper, so it's going to cost more money. So what they do is they have a source of radiation, so something in here that is unstable. This will decay. As it decays, the radiation will travel through the paper. Now the paper is sort of being fed between these 2 rollers here and here, and these 2 rollers, what they can do is they can get closer or they can get further apart in order to increase or decrease the width of the paper. So what happens is the source goes through and it's detected on the other side here. Now if the paper's too thick, that's going to mean that you're going to reduce the amount of radiation that's going to be detected by the detector. So if the amount of radiation decreases below a set amount, this detector here will tell these rollers here to get closer together, because as I said, the paper's too thick, which means the radiation detected is too low, so the rollers will get close together to make the paper thinner. Now if we look at the opposite, if you have lots of radiation going through, the intensity of the radiation is increased, that means that the paper is too thin, so the rollers will therefore move apart and make the paper thicker. So we're going to think, what type of radiation would you use? Alpha, beta, gamma? Well, alpha, not going to be that useful. Alpha's stopped by paper, very thin paper as well, it wouldn't make a difference. Gamma, well, gamma's only reduced by lead in concrete, so a bit of paper is not going to be any problem for that. It won't have any effect reducing the radiation. Beta. Now, I know we've talked about aluminium being the thing that stops beta, but if it passes through paper, it would reduce the amount of radiation going through it. And if that paper's thicker, it will reduce it even more. So we use beta for this. Now this one here is for something called irradiation. What we're doing is we're using it for treating tumours. It's a bit of a weird one because people think, how on earth can you use radiation to cure cancer, if you like? We've just said in a few sessions ago that radiation can cause cancer by ionizing atoms in DNA and causing mutations. Well, think of it like this. This radiation, if it keeps going into the body and keeps damaging the cells, it will damage it so much that it destroys them. So what we do is we focus the radiation here onto the tumor, and the radiation will destroy the cancerous cells. Now this is called radiotherapy. Some people get it a bit confused with chemotherapy. Chemotherapy is different. Chemotherapy is where they use a certain drug in order to treat the cancer. This here is where we expose the tumor, the cancerous cells, to radiation. So now what we're going to think of is what type of radiation we're going to use, alpha, beta, or gamma. Well, we can't use alpha. Alpha is very ionizing, which you could say is a good thing, because it means that it would damage the cells very, very easily. The problem is alpha is blocked by things like skin. So if you've got a tumor that's in the body, it's just going to be blocked by the outer layer of skin. And then it's just going to ionize the outside layer, therefore leading to something like skin cancer. So alpha's a no-go. Beta. Beta is better. It can penetrate more and it's more ionizing, but probably won't be able to go through deep enough. Gamma is what they use. Now, they might actually use something like X-rays instead. There is a reason why. They're both similar to each other. Gamma is slightly more energy than X-rays. The only advantage is with X-rays, we make X-rays using a very high voltage electric circuit. So instead of having something like a gamma source near a patient emitting gamma radiation that's very difficult to focus, they might use something like X-rays, similar to gamma, that we can control and we can focus. But anyway, the reason why they use this is because it's quite weakly ionizing, but it can travel through more of the body. Therefore, be able to penetrate the layers of tissue in order to get to the tumor. Now, when they use radiotherapy, they might either just expose the tumor from one side, or what they can do is that they will rotate this round the body. It's something called a gamma knife. And it means that, let's say the tumor is right here in the center. It means that that tumor is going to be exposed to that radiation all the way around. But at least the other healthy cells aren't going to be exposed to as much. So instead of, if we just had the gamma focus down here, all of these cells in the way are going to be exposed to gamma. They're going to have as much radiation as the tumor here. So if we rotate it around, always focused on the tumor is going to have more of the radiation, and these healthy cells on the outside will have less radiation. What they usually do as well is, instead of doing this in one go, in having one session of radiotherapy, you'll have many sessions of radiotherapy, and they'll give you a bit of time between each session in order for these healthy cells to recover. They've got to be careful on these types of things. Obviously, if you've got organs that are more susceptible to radiation, to mutations, they've got to be careful on where they use radiotherapy. What they can also do is they can use things like gamma and they can use X-rays to sterilize equipment. So if you have hospital equipment, obviously they'll wash it after they're used, but if you've got things like bacteria on there, something really difficult to kill, then they'll expose these to things like things like gamma radiation or maybe even X-rays. Right, radioactive tracers. Now, with a tracer, what they will do is they will inject the body with something that is radioactive, i.e. something that's going to decay by alpha, beta, or gamma. That will go into the body. What they usually use is a fluorine isotope that binds onto the glucose. And what happens is that will travel around the body, and as it travels, it will start decaying. Now, there's two types that they use. There's one that's a more advanced A-level answer, but in simple terms, it gives out gamma radiation. And what you do is around the patient, once they've had this radioactive tracer injected into them, they will put the patient in a gamma detector. You may have seen it before on one of the scanners. It basically looks like a big polo and the person moves through it. And what will happen is that wherever the blood's gone, the glucose has gone, or wherever the radioactive tracer's gone, it will then start decaying and it will give out gamma radiation. The scanner will pick up this gamma radiation, and what it can do is it can tell you where it is, and it can tell you by looking at the intensity what organ it's in. So what you can do is you can build up quite a good image of things like where's the blood going in particular, things like tumours. Tumours are going to have lots of respiration going on because there's lots of mitosis, lots of cell growth. So because of that, you're going to have lots of glucose going to it and a good blood supply. Maybe you can use it for other things as well, just to see where the blood's going, but that's just a good example of it. The good thing about gamma for this one is that gamma is very low ionizing strength. So if it's in the body, it's not going to damage the cells very much at all. Another thing is that because gamma is reduced by things like concrete and lead, i.e. can penetrate through a lot of different materials, it can get out of the body no problem. Alpha or beta wouldn't be able to get out of the body, and if it did, it would damage you on the way. Now, when you're using this sort of isotope, what you'd also do is you'd have something that's got a very, very short half-life. When I say very short, I mean relatively short. So something like a couple of hours to a couple of days. You want it long enough so that this process can happen. You can make the scan, but you don't want it too long so it's in the body for that long as well. Another use for radioactive tracers is something like this. So they can use this to work out if there's a blockage in a water pipe or if there's a leak in a water pipe, etc. What they will do is they will put a chemical in the water that will decay and give out radiation. Now, let's say we've got a blockage here. This water over here will have the radioisotope in it that is radioactive. If you've got a blockage, not much water is going to go by. So this person on the surface, what they're going to do is they're going to know where the water pipes are. They're going to pick up any radiation on here with something like a Geiger counter. And what they can do is they can pick up where the radiation is coming out. Now you've got to think, what type of radiation we're going to use? Alpha, well, the alpha wouldn't be able to get through the pipe in the first place. The beta, well, probably not. Gamma. So what happens is that when this water with the radioactive isotope in decays, the gamma goes up because it's only reduced by things like lead and concrete. You can get through the mud no problem, and the person on the top is going to be able to detect this radiation. Now when you get to the blockage, you're only going to be having a little bit of water coming out the other end. So they're going to notice a very high decrease in the radiation on the other side. So what they can do is they can therefore note where exactly the blockage is, because that is where the levels of radiation have decreased. For a block pipe, for a leaking pipe, it's something very similar. For a leaking pipe, you can have water leaking out all over here. They will notice a high level of radiation around where the leak's going to be. A couple more things about this. Why is it useful? Well, otherwise, if they're not sure where the leak is, they're going to have to dig up more of the road. That's going to cost more money. That's going to cause more of a disturbance. So this will be more efficient. Another thing is that the radioactive isotope is going to have a relatively short half-life. Just like the tracer, we don't want it to be radioactive for very long. So when people drink this, it won't be in their body for very long. Plus, it's very weakly ionizing. So if it does get drunk by a person, it will be very weakly ionizing. It shouldn't cause much damage at all, if any. Final one, smoke alarm. Most people are quite surprised to hear that smoke alarms have something that is radioactive inside. It's in this bit. Sorry for giving you tips about where to get a radioactive isotope from, but it's in here. They use americium, and essentially in here you can see there are little gaps there. The gaps is to allow air to go into it. Now some people again are thinking, how is that safe? Something that's radioactive is in my house. Surely that's not right. Well, first off, let's have a look at how it works, and then we'll look at how this is actually safe. So what you have is you have an electric circuit. Electric circuit is connected to an alarm. Now in this electric circuit there is a gap. So here's the gap here, there's the gap there. Now air is allowed to pass through this gap, but also is exposed to radiation. This radiation is alpha. Now as we said before, alpha is incredibly ionizing. It's very good at removing electrons from the outside of an atom. So what will happen is this alpha radiation will go in here. So the alpha radiation will go into here, and it will collide into particles that make up the air. When it does, it will ionize them, i.e. releasing electrons and turning the atoms into ions. Now the electrons will move one way around the circuit, so they'll move that way, and the ions, i.e. the positive ions, the nucleus and the remaining electrons will move the other way. Now essentially what you've got there is a flow of charge, i.e. a current. Now this current will move around the circuit, causing the circuit not to go off. It will have a detector here, and basically when this detector detects a current, it won't set off the alarm. But as soon as there's a fire, and as soon as there's smoke in the way, The smoke will go in via these gaps here. And when they go into these gaps, they'll go into these bits here, and the smoke particles will block the alpha radiation. Remember, alpha radiation has a very, very short range, so it can't travel very far. And once it starts blocking the alpha radiation, you have got less ionization going on, therefore you have got a current reduction going on. Current reduction is detected by this detector here, and when it's detected by the detector that it's decreasing, the alarm will go off. So how is this safe to use? Well, go back to this, look at what it's surrounded in. Aluminium, so it shouldn't be able to get out. Plus, smoke alarm is on the ceiling, so if some did come out, it only has a range of a few centimeters. So as long as you haven't got your mouth up to the smoke alarm inhaling away, you're all good. Bit of a problem with smoke alarms is the disposal of them. People forget or don't even know that they contain anything radioactive. So when they're broken or when they stop working, people will just throw them away. Therefore, what you're doing is you're not disposing of the radioactive isotope properly. This can be a problem. Right, enjoy guys, see you in a bit.